And the idea of this language model is to understand the word sequences. Okay, the word order. Your LSTM model is going to understand after this word, what is the probability of this word? Okay, if these two words happen, what is the probability of the next word? If these three words are happen, what is the probability of this? That is how logically we can interpret each state of your y cap of 1, y cap of 2, y cap of 3, and so on. Suppose I have a sentence, something like this. For the case study, I have taken very commonly used email conversations. I have taken email conversation. Maybe you can change the data type and you can give any other database you can use. In fact, most of the conversation it is taken from my own personal email. What are all the whenever I try to reply, what are all the very frequent sentences I use from my sent box itself? I have taken some of the sentences. Just I'm going to show you some snapshot of that. So there is no limitation of number of sentences you wanted to train. There's no limitation. So I have taken a few sentences. Okay. If you wanted to train with a few more large volume of data set, also you can train. So look at the some of the conversation I have taken. Each one should be treated as a separate sentences. And here directly I have written all the sentences using \n, or you can load all the text in the form of .txt file, and also you can extract each line. Okay. So whichever the way you wanted to do that, you can do. So look at most of these are all the common email conversations that what you see. Nice to hear from you, right? So kindly call me whenever you are free. These are all commonly used conversations in the email. I would like to discuss possible training sessions with your organization. Sorry for the late response. Okay, we shall connect today evening. Meanwhile, if I need any clarification, I shall reach out to you. So likewise, so I have taken some of the commonly used sentences in the email conversation. Say, for example, the sentence nice to hear from you. Your language model, the purpose of the language model need to understand the sentence order. And again, how you are going to prepare the input and output representation. You can, the very basic, I'm going to give you some different way I have prepared the input and output, and to appreciate the performance of each representation. See, for example, model 1, I'm going to consider one word input, one word output. One word input, it's a vanilla model. Okay, one word input, one word output. There is no language order. It's a one-to-one mapping. Something like your numerical data, like predicting today's temperature based on just yesterday temperature. That is a one-to-one model. So in the context of numerical data, people call this one-to-one. One word input or one value input, one value output. It's called as a baseline model, or even we can call this as a null model. So today's temperature based on yesterday temperature. Okay, I should not use the word null model. There is one more variation is there for the null model. Null model is like there is no, in fact, there is no modeling. In fact, say today is Saturday, okay, Sunday, and this is Friday. The null model will be behaving like this. I wanted to predict today's temperature. Okay, Saturday temperature. I would say that Saturday temperature is same as the Friday temperature. That is null model. I wanted to predict Sunday temperature. Sunday temperature is same as the Saturday temperature. That is what the null model in the time series. There is no intelligence, isn't it? There is no intelligence. Simply I'm saying that yesterday temperature is today temperature, but it will be very closer. Okay, mostly it will follow very close, but there is no such thing like a model coefficients. Nothing I'm going to use it for the training. So in fact, it is no model parameters are involved in this. We call this as a null model. But however, this is not a null model, but it is taking one previous token into account based on that model is done. In fact, there is no sentence order, right? It has to just memorize one token. For this token, what should be the output token? Okay, if this input token is there, what is the output token? There is no contextual the meaning of the word order and all. These model, it's no need to bother about it. So that is a very simplified representation. One word input and one word output. So we people call this a vanilla model. Then you can consider the word maybe 3 tokens input, okay, and 1 token output. So you can say, for example, nice to hear. Okay, for example, I'm preparing the input sequence like this. If the input sequence is like this, nice to hear. So what is the next token to be predicted in the output? So nice to hear from the token from should have the highest probability out of the remaining words in the vocabulary. So according to your database, whatever the training records you are going to train, first of all, you have to figure it out how many unique tokens are there in your corpus. Corpus means in your training records. So in our corpus, I have taken, see, nice is 1 token, 2 is 1 unique token, here is 1 unique token. We have to see, we have to first collect the unique number of tokens. Once I collect the unique number of tokens, then each token, okay, each token will be given unique identifier. Unique identifier, that is the integer representation. So we have a function to do that. We no need to do it manually. That process is called tokenize. Okay, the moment you do the tokenize, it is going to allocate unique numerical identifier for it. For example, for the word nice, it is say for example, it allots some integer value 7. Okay, for some other token, this is for the nice, and we are going to shortly see that actually what value it is going to assign for it. For example, sorry, it may assign some other token, something like 12. This is just an integer value. So this is the first step process. It's next step only. Okay, now each token, for example, nice is represented as in the form of word embedding. Each and every token will be represented as a word embedding. Again, here we have a choice. I'm going to use a Keras layer word embedding itself. Here, the standard, most of the state-of-the-art application people go for the 100 by 1 representation. And here my corpus volume is not so high. Even I can represent each token with a 10 by 1 representation. Even it is doing a great job. Okay, if you are going to have a more volume of your corpus, say number of unique words is 1 lakh or 10 lakhs, 1 million unique words and all. Maybe you have to more refinedly define your token with a 100 by 1 vector. But in this example, I'm going to consider 10 by 1. If the quality of the result is not so great, you can increase that word embedding, number of features to represent each word. Say, for example, if the two words are coming very close meaning, if you want to represent that word with more number of features, so in the word embedding layer, you can increase the representation size. Okay, these are all things we can modify in our part of the hyperparameter. So in general, what is your language model? The purpose of the language model is to, whenever I'm talking about the language model, it is equivalently applicable for the, it's a simple forecasting problem. What we say a forecasting problem for the numerical data, I can forecast tomorrow's temperature. I can forecast tomorrow's the stock value of a particular product. You can forecast the rainfall. Any time series numerical value, how do you put into a forecasting problem? Similarly, your word sequence, this is a nothing but a word sequence forecasting. The word sequence forecasting problem is called as, in NLP terminology, you should understand, that is a language model. Language model. You can create this language model for any language. Okay, like English, you can create it for any language. So basically, your tokenize is going to convert each and every token. Okay, each and every token in the form of a numerical value. Like a numerical value 7, and this numerical value is converted into a 100 by 1 feature vector. So that process you can do it for any language. So the idea of the language model is it has to understand the order of the words. After this word, what is the probability of the next word should come. So after nice, okay, after nice, in general, in our English sentence, after nice, nice B, it won't be a proper grammar, right? Nice B, nice two, nice V, nice free. All possibilities are there, right? Out of all these cases, which token it's going to have the highest probability? So in terms of a probability sense, it will be treated something like a conditional probability, isn't it? So how do you perceive this as a conditional probability? Once the nice token is given as x of 1, okay, this is what the target, actual target you have given. After, of course, you have given the target for each one. We have given the target for nice. The next will be taken as the next token will be taken as the 2. But model will give, for the initial randomly initialized weight value, the model will give some random probability score, and the loss function, it will try to minimize the overall loss function. At each y of 1, your loss 1 will be computed, and y of 2, your loss will be calculated, and the total loss, your algorithm will try to minimize the total loss. But at each and every individual y of 1, how this calculation can be considered something like a conditional probability, something like this. What is the probability of 2, okay, given a nice? Okay, that is how my y cap of 1 will look at the score. Okay, it will try to calculate like this. What is the probability of 2 given nice? So how y cap of 2 will perceive the input? Your y cap of 2 will perceive the value something like this. What is the probability of, okay, what is the probability of here given a nice and 2? Because already 2 tokens are in the order, right? Because x of 1, this is nice, x of 2, it is nice, 2 tokens are given. In fact, this is y of 3. So given nice and 2, what is the probability of here? And for this guy, what is the probability of from, okay, given a nice to here? So as the length of the sentences keep increases, that is the problem of long-term memory issues we have, we encounter that. That is why we are using LSTM. So LSTM will keep track of the longest sequences in the form of cell state, as well as the cell state is indicated as C of t, as well as the A of t. So A of t in the RNN with respect to RNN terminology. Okay, with respect to RNN terminology, A of t is called as, it's represented as a hidden state in general. In general, hidden state. Hidden state also, it is a memory. Okay, it's the memory of the sequence. In fact, to be very specific, the memory of the past sequence. So we have an issue of the memory of the past sequences with RNN when the length of the sequences increases, because the probability of this value prediction, this will be not so accurate if the length of the sequences go very higher. If I keep dependent only on A of t, for that notion, we went for gated recurrent unit and LSTM unit. So in GRU, we are managing the same like A of t in the form of C of t, but the C of t we played very dynamically. Okay, for the past t minus 1, what should be the scaling factor? How much importance I should give? For the current memory, okay, the memory unit for the current token, what should be the scaling factor? It handles the memory unit in a dynamic fashion, not in a fixed manner. Like one step ahead, your LSTM is going to handle the scaling factor with a different gating mechanism. Why you are using a one single gating mechanism for this guy and this guy? Let us use a different gating mechanism for this and this. In fact, one more extra gating mechanism for the short-term memory. Two different gating mechanisms for the long-term memory. So even you don't need to even explain. It is very hard to explain. If any question people try to ask you in the interview in the LSTM and all, you may not explain the mathematics, which is the best way to explain what is the difference between RNN and the LSTM or gated recurrent unit. The best way to explain about this without complicating the stuff is RNN having a static memory, whereas your LSTM and GRU having a dynamic. And very specifically, LSTM understand the long sequences in the form of long-term memory. Your cell state is holding the long-term memory. Okay, in general, we call this AT is a hidden state. It is keep track of the short-term memory. Whereas GRU is remembering both short-term memory and long-term memory with only one cell state. Okay, by using the sigmoidal gate function called update gate function. So using one gate function, it is updating CT minus 1 and CT. So the same CT is acting as a long-term memory as well as the short-term memory. Whereas in the LSTM, we have a separate entity for a long-term memory. C of T is the entity for the long-term memory, and A of T is the entity for the short-term memory. In this way, if you explain, this is more than enough. So nobody is going to ask you, give me the equation of CT and what is the equation of YT. Even if they ask you, it's not a big deal. You know how to represent CT. CT is a function of at every time your CT minus 1 times your XT, your current term. So weighted by your weight matrix plus the bias term. So based on your CT, your YT is calculated based on WY weight matrix, and this CT is going to scale with the separate weight matrix to yield the output. This is a basic relationship. This basic relationship we are extending for the multiple gates. So for the GRU, we are using one tau U. Okay, whereas for the LSTM, we are using tau F. For the forget gate, tau U. So forget and update gate. And additionally, I'll be using the output gate. Output gate for the short-term memory for AT, the scaled version of AT. So now let us focus on the implementation. In the implementation, what are all the different way I can prepare the input and output? So the first type of representation I'm going to use one word input and one word output. We call this a vanilla architecture. It's there is no complex word order, isn't it? So every time there is x of t, and you are going to train the model for y of t. Just one single token. So in this architecture, I don't have xt plus 1, I don't have xt plus 2, and so on. It is at one instant. Okay, one token input. What is the one token output? It's a very simple architecture. This model is called as a vanilla architecture. Vanilla LSTM. There is no word order. Of course, there is even I don't require LSTM for this. In fact, even your RNN model itself do a wonderful job for it. Just for the comparative analysis of the results, I am going to use some 2 to 3 different variation of the architecture. We are going to appreciate which architecture is outperformed which architecture. Definitely, this is not going to be a great architecture. Just for the comparative analysis, I have taken very simple vanilla model. So let us understand what are all the libraries I'm going to use for this application. Before that, let me share this file with you. This is S13 notebook. Okay, can download it. So in this library, which are the things new to you is, I think, tokenizer. We have not used it before. And this embedding layer. And sequential dense LSTM is, and of course LSTM. LSTM is our model. So LSTM is part of the layer, and even embedding is also it's a part of the layer. Before your data enters your model, it has to pass on to the embedding layer. So what is the role of the embedding layer is to give you each token will be represented with the standard feature vector representation. In the subsequent exercise, in another case study, I will show you how you can use the some third-party embedding, word embedding. Also, you can use like Gensim, Glow. So there are different Facebook. They have their own word embedding. So one company to another company, maybe they little bit fine-tuned on the feature representation. Some word embedding are more. We talked about gender biases and racial biases, geographical biases, maybe there. So you can free to use some third-party word embedding layer also. But here in this exercise, I'm going to use the standard Keras layer embedding itself. I'm going to use the subsequent exercise. I think many to many encoder decoder model. I will be showing how to use some external embedding. So how many sentences you wanted to train? You take all the sentences. Okay, here it's a small chunk I wanted to demonstrate. I have taken it here. In case if you are using a very large volume, better you keep it as an external file and then you can load it. In fact, for the next case study, I'll be loading the entire training record from the external files, because we'll be having roughly around close to more than 10,000 sentences we'll be using it for the next case study. So here I have a small representation. So I just directly I have given all the sentences here. So now what is the steps you have to take care when you do the data preparation? So first you create an object for tokenizer. What is the role of the tokenizer? Tokenizer, it is going to give you the encoded representation of each token with a numerical integer encoding it is going to do. So it is one step process. It is doing data cleaning in case if any comma, punctuations and all is there. It will do the basic data cleaning, but it does not do English stop word filtering. Whereas if I treat this using TF-IDF vectorizer or count vectorizer, by default it will do English stop word filtering. And there also you can control whether you wanted to do the English stop word filtering or not. That also you can. If you want to filter, you can give an argument. Otherwise, you can skip the English stop word filtering, even when you do the TF-IDF vectorizer. But here we are not going to represent each token as TF-IDF vectorizer, because we wanted to memorize the word order. That is the focus here. The word order is very important. Here my focus is not to memorize the keywords. Your news group exercise, we have used the TF-IDF representation, because there the news article I wanted to memorize some of the keywords related to political news, science and medicine, religious news, and sports news. So since it is a language model, I am going with the simple tokenizer. Simple tokenizer, the role of the simple tokenizer is just to assign the numerical value. Just simply tokenize and give a numerical integer value to it. So we create a tokenizer object. So using the tokenizer object dot fit on text. Here you pass your data training samples. So fit on text, and based on the white space, it will consider each and every the moment it sees the white space. Okay, that is the end of the word, right? It will recognize that is the end of the word. So that will be registered as one token. After the white space, it will consider this as another token. Another token. So actually, our first token is nice to hear from you, right? Let me run this and I'll show you. Okay, for nice token, it is allotted integer value 29. Okay, and for the token 2, it is allotted the integer value 1. Here it is 30 from 31. U 2. So again, you could see this next sentence I am having U. Okay, for U it is allotted 2, right? So can you see the next sentence 2 is appearing again? So 2 is appearing here. So the tokenizer will understand each and every token with some integer value. Okay, this is just an integer representation. It will tokenize and it's going to allocate integer representation for the each token. So that you can visualize in the encoder. So it is followed by two-step process. First fit on text followed by tokenizer dot text to sequences. It's a two-step process, a two-stage process you have to do this. So it is simply tokenize it. So the next one, it is going to allocate the integer value to each token. So the integer value is allocated to the each token. See, for all. Let us check what is the length of our training data. That in terms of number of tokens. In terms of number of tokens, the length is 143. Out of this 143 tokens, there are many tokens may repeat, isn't it? Say for example, U is appearing again. I, many times I is appearing, capital I. So don't worry, this tokenize function will take care of, okay, whether I use kindly in the beginning of the sentence, okay, the beginning of the sentence capital K kindly, and somewhere in the middle of the sentence this kindly will be given the same integer value that will be taken care by the tokenize. Okay, so that process also, all the tokens it will start with a lowercase, then only it is going to allocate unique integer value for it. So that will be taken care by the tokenize function. So now I'm going to ask the tokenize function, how many unique tokens are there out of the total 143 tokens here? So unique tokens are 85. Okay, how do we get that? You can access the tokenizer with a method called word underscore index. Now you can see for each unique word, okay, each unique word, what value is given. What is the word index allotted to the each unique word? That you can see 1, 2, 3, 4 is being allotted for your training record like this manner. So maximum is 84, isn't it? So 84 is the maximum integer value it's represented. I have to represent this in terms of a Python index starts with 0. Okay, I wanted to keep my vocabulary size is 85. So I will pass this vocabulary size as the upper limit. Anyhow, Python index will not consider the upper index, so it will access up to 82. So for that reason, I just put +1 for my. I wanted to, whenever I wanted to refer hereafter in terms of the Python index, I will represent this with index number 1 and goes on. Upper limit, I'll say 85. So upper limit starting with the index 1, it is going to consider the token 2. Okay, what is the last index I should represent? 84, right? Because only if I give the upper limit 85, Python will go and access up to 84. Upper index -1. For that reason, I'm adding 1, and I keep my vocabulary size is 85. Okay, this is just for the Pythonic indexing purpose. But otherwise, you have a unique number of tokens are 84. So tokenizer dot word index, simply if you put the length for this, only for the unique words, it is allocating the integer value. So it returns 84. If you want to see the individual, each and every token, what integer value is allotted, you can simply visualize like this. Tokenizer dot word underscore index. So in the next cell, we are just counting the number of unique tokens, okay, in the variable vocab size, vocabulary size. Can you tell me what is the size of your output y cap of t? What will be the size of y cap of t? What is the size of y cap of t? Size of y cap of t is 1/hot representation of 84 unique vocabulary, isn't it? 1/hot representation of this 84 unique vocabulary. Suppose if you suppose my input, if I prepare my input in such a way that 3 token input, I'm preparing the data like this, 3 token input, nice, or even 2 token input. Suppose a 2 token input I present. When I present 2 token input to the model, while during the training, how I have trained this? I have trained a 2 token input model will be trained like this, nice. The output to the target is given as 2. Next, this initially it will use a t minus 1, okay, as a 0 vector, as well as c t minus 1 as a 0 vector it uses, and this guy will compute a t as well as the c t to compute. Then 2 will be given as the input, next token x of 1. This is x of 2. This is being trained for here, right? Here. Assume that if it is a 2 token input and my output is here, this is how I have trained it. If I prepared my length of the input sequence is 2 tokens. We can also prepare the length of the input sequences, maybe 3 tokens or 4 tokens, whichever the way you wanted to train, we can train. If I have trained it like this, 2 token, if these 2 tokens comes together, your model will already learn in such a way that we have increased we have trained this model in such a way that, okay, the probability of here, okay, given a nice and 2 was already trained for the higher probability. So in a production environment, when you try to give nice and 2 as the input token, what is the which token is going to have the highest probability after these 2 tokens? It is trying to give a autocomplete for you. That is how your language model is trying to work. So the next step is I have to prepare my input and output. Okay, this portion is very crucial. How, according to your requirement, how do you prepare your representation, input and output representation? So first is our attempt is the vanilla model. Okay, 1 word input, 1 word output. There is no word sequence. It is a simple 1-to-1 mapping. So we are creating a word-to-word sequence, 1 word input, 1 word output sequence. So put together all, how many possible representation can be created is, as you can see that how after tokenization you can see, okay, when 29 is given as the input, okay, 1 should be acted as the output. Okay, 29 is the input. 29 is the input. The corresponding output should be 1. When I feed 1 as the input, the corresponding output should be 30. When I feed 30 as the input, the corresponding output is 31. This way, okay, this way I have to prepare my input and output for each sentence I have to prepare. Okay, each sentence I need to prepare. So this loop is going to create that. So for our training records, how many such one-to-one mapping can be performed for our training records? The total number of tokens were 143. Okay, out of these 143, how many such sentences you can create one-to-one? You can see 29 is given as an input, 1 is out. Just now we wrote this. Then 1 is the input. What is the output? Is 30. 30 is the input. 31 is the output. Likewise, how many combinations we can create per sentence? So each sentence. So we create this by initializing an empty list, and I'm running a for loop for I in range 1 to length of the encoder. So already we have seen the length of the encoder is 143, right? So it will go up to that. So the starting index of I is 1. So from the encoded, so encoded list, in encoded list, you have 29, 1, 30, 31, and so on. So what it is doing, encoded square bracket I minus 1. That means from the encoded square bracket I minus 1 is 1 minus 1. The index starts with 0. At the 0th index, colon I plus 1. I plus 1 is 2. So 0 colon 2. In Python, 0 colon 2 will access 0 colon 1. So these two guys will be accessed. In the next instant of I will be incremented to 2. In the next instance, these two guys will be picked. Okay. So first I'm creating the pair. Then I'm going to say that, hey, you have to act as X, you have to act as Y. So that in the next step, I can define that. First, which from the entire tokens, you have to say that how many tokens you wanted to use as an input. Say, for example, next time, if you wanted to create something like 3 token input and 1 token output, that kind of data representation you wanted to create. So in that case, I should access these 4 guys. I should access. Then I can say, okay, 3 token input, 1 token output. This way, we can prepare the input and output. So it's not necessarily that you could create a input output representation with equal length. Okay, even in fact, the second modeling approach, I have used even unequal length, including how or, okay, this is one representation. Another input I can represent like this. How are you? This is the second input. Nice to, then nice to here, nice to hear from, nice to hear from you. This way also you can create input output representation with the variable size. But when you create input output representation with the variable size, make sure that you have to see which is the longest sequence you are generating. You have to pad, see, for example, in this example, 1, 2, 3, 4 tokens. 4 token is the longest sentence, right? So I have to pad with the zeros according to the longest sentence of your input. So this representation, you have to do it whenever you are creating the input sequences with the variable sizes. So 1, 2, 3, 4 tokens are there. So that is a padded with 1 0. Here it's padded with 2 zeros, padded with 3 zeros. So this padding we can do using a functionality called pad sequence. But here, however, padding is not required because we are just creating a 1 token input, 1 token output. Okay, there is no scope for padding. In fact, it's a vanilla model. So the next step, what I do, I split what is my X, I say what is Y. So the entire sequences you are going to put in NumPy array, and you are saying that all the records in 0th index is my X. In the index number 1 is my Y. You represent X and Y, you represent. Okay, look at this. This is what I was asking you as a quiz question. I asked you what is the size of Y. Okay, just 5 minutes before or 10 minutes before I asked this question. Your size of Y is based on your vocabulary size. Okay, number of classes is based on the vocabulary size. So we perform one hot encoding for the output. Y is being done one hot encoding. Okay, look at your modeling part. It's just hardly 3 to 4 lines of code. So again, this particular application, I don't require any functional design. Maybe the next implementation, encoder decoder representation, we may require a functional design. And soon you'll realize it why. Here we are going to do the sequential design. So model is defined as usual with sequential. Look at the very first layer I'm adding is an embedding layer. So for each vocabulary, okay, so how this embedding layer is going to create, whatever the number of vocabulary in your training, each unique token, it is going to create a matrix, something like this. Look at the size of the vector, the embedding layer vector I'm giving here is a 10. Again, this is the choice. You can give it as a 30, 40, 50. Just like the number of neurons in the LSTM layer, you have a choice. Here also, your each token representation, you can represent. Here I'm going to represent as a 10 by 1 vector. This is token 1, token 2 is represented by 10 by 1 vector. Token 3, how many unique tokens are there? That many unique tokens we are going to represent as 10 by 1 vector. Also, you have to tell what is the length of the input sequence. What is the length of the input sequence? In this case, we have prepared one input, one output. So the length of the input sequence is 1. Okay, so that information also you have to specify. So your embedding layer is defined. You have defined the embedding layer. Once you have defined the embedding layer, I'm defining the LSTM unit. Sometimes, if you are using some external embedding, okay, if you use some third-party embedding, you, as part of the data preparation, you will be completing the embedding also. Okay, then in your model building, once you define model equivalent to sequential, the very first layer itself you are going to add model.add. Okay, your LSTM will come into picture. So since your LSTM is the very first layer is going to act as your LSTM is going to act as the very first layer. Here you have to specify the input. What is the input shape you have to tell? That is a general rule in any deep learning architecture, isn't it? Whether you start with the CNN layer means you have to specify what is the size of your input. Right from the MNIST data set, we have seen 784. When we vectorized 28 cross 28 as a 1 dimension. Then we presented the input as a 2-dimensional form. So the very first convolution layer, 2D, we represented the sizes to 28, 28. Then for malarial data, 28, 28, 3. If it is a dense layer, suppose your very first layer is a dense layer, and you are going to use a hidden layer. So dense 50 neurons, and you have to specify what is the input shape. So in your deep learning architecture, whichever is the first layer, it is mandatory to specify the input length. Okay. Suppose if you have done the embedding as a third-party package, you have externally have done the embedding process. This line won't be there. This line won't be there. So your first layer itself LSTM. Here I should specify the input length of the input. Okay, that kind of design also is part of Subsequent exercise, you'll be seeing it. What will be the values inside? It's a feature representation. We have seen like a king, queen example, orange, apple, the word to it. So there are it takes some feature represents each token with a combination of certain feature vector. What is the probability of being a noun? What is the probability of being an article? What is the probability of being a verb? So it is giving some weighting factor for each token, and it is represented as a 10 by 1 or 20 by 1. Hope you remember the slide as part of able to recollect with Vijay. We have gender as one feature, and we have whether it's an animal, whether it's a fruit, whether it is a geographical location, or it is a noun, or it is a pronoun, or it is a verb, or it's an adverb. For each standard feature representation, some weighting value will be given for each token. That is the role of the embedding layer. Typically, we cannot see this. We use a PCA technique to visualize this, but I told you a PCA technique is not the apt way to actually visualize the word embedding representation. In fact, the original paper, I told you one of the transformation. I think I told you, yeah, the name of the transformation is TSNE. TSNE algorithm. They have used to represent whatever the embedded feature representation for the visualization purpose. Whatever the visualization we see in most of the literatures, like king, queen will be at one side, men, woman, and trouser, shirt. These are all the clothing items, right? And numbers like 1, 2, 3 will be here at one space. In a multidimensional feature space, where is the location of each token? So it is placed in a meaningful locations, like all fruits will be at one location, orange, apple, banana, and all. Its model will understand these guys are having a similar characteristics. All action verbs will be at one location. All pronouns will be at one locations. Likewise.
So then what is the difference between 10 to 1 and 100:1?
It uses the choice of refined features. How many features you want to? The same token can be represented with the 10 features, the same. Based on the top, it will automatically prioritize. See, because each feature has a certain weighting factor, right? You are asking, represent my token with the top 10 features. Represent my token with the top 20 features. Represent my token with the top 30. It's your choice. If I represent my each token with 100 features, means you are using more features to represent one token or less feature to represent one token.
Okay, so if nice to hear from you is a sentence, if you take nice, then the nice can be represented in 100 different features, right? If you give 100.
Yeah, the nice token is represented by here. I have given 10 tokens.
Correct.
But if you say 100 means the same nice token be represented by 100 by 1.
Okay.
Whether nice is part of a fruit? No, nice is not part of fruit. Whether nice is a part of a geographical location? No, nice is not part of a geography.
Okay.
So if you feel that your corpus is too complex and the many tokens are coming very close to each other, if you find that kind of refinement is needed for each token, maybe you can represent with more feature representation. Because our corpus is very simple, so I don't require, okay, nice, given the top 10 feature would have a very good representation of the nice. I believe it. That is why I taken 10.
Okay.
Okay, if you are not happy with the result, if you see the for example, after these word sequences, you are expecting some word here, but your model is giving some other word. Maybe this word also very close resemblance. Maybe you may think that, okay, 10 feature vector is not representation. Here is not good. Maybe I'll go for 50 representation, or maybe 100. When I use 100 representation, this is what you expect, but earlier model was giving this token. Maybe after increasing your representation to 100, maybe this time it is going to give this representation. It's all about how many feature representation you are going to use it to represent each.
Okay.
Yeah, but we are not giving the nice directly, right? We are tokenizing it into numbers and then giving it. Outcome it will be represented.
Yeah, that mapping is there, no, but internally it has its mapping. See here. For nice, it is already related to each token. This mapping is there. This mapping is maintained. It's not a random number. So that
Okay,
is the
so
order. Your embedding layer first it will embedding layer will see that, oh, you are 26. Okay, who is 26? It will see. Okay, is
oh, okay, internally
so,
it does it. Okay.
yeah, yeah. Internally it will understand for internal representation. So that is the reason we don't specify the input length in the LSTM layer, because actually your embedding layer is acting as the first layer here in the sequential order. That is why the length of the input sequence we have given here, length is 1. In case if you have done the external embedding process, your LSTM, after this LSTM number of neurons, input length I should specify here. So naturally the question will come, why you have not specified generally the input shape we specify here, why we are not specific. The reason is because first your each token is going through the embedding followed by LSTM. So the size of LSTM is 50 means the size of your AT vector and the size of your CT vector is 50 by 1. That is the meaning of 50 neurons. So again, this is the choice is based on, okay, the complexity, how you wanted to represent your hidden state, your short-term memory and long-term memory with how many neuronal units you wanted to memorize it. If it is a too complex sequences, maybe you can require more number of memory units to memorize the sequences. After all, here my sentences are very short sentence. Even in the next model, if I create multiple token input, maximum I may not go more than 10 tokens. Okay, within the 10 tokens. So with LSTM 50 memory units, I start with randomly. You have to start with some number. Then if you're not happy with the convergence of the loss, you have to increase. Okay, what are all the attributes here you can experiment is increase your memory units, just like how do you increase your dense layer neurons. Same manner you can increase this. Also, as I told you that for a particular sentence, you are expecting some word to be filled here, but you are expecting another closer word. But this one, you look, this one is more appropriate if you feel. Maybe your word, your feature representation is may not sufficient to refinely predict that. Maybe you can increase this representation. So mainly these are all the two variables you can play around and to achieve the required level of efficiency, whatever you want. Your output layer is one hot representation of your vocab size. With activation softmax. So it is, you know that we have used for the MNIST data set, what is the dense layer we have given? 10 neurons, isn't it? 10 neurons. So when you present the data in the form of X and Y, make sure that this Y should be one hot input. Here it is enough to tell the number of classes. If it's a binary class, in the dense layer, you have to specify 2 classes. So I'm specifying the vocabulary size as the number of units. Anyhow, when you present the Y, Y is already been one hot input. Look at your, what is this 10 by 1? 10 by 1 is the size of your each token. X of t representation is 10 by 1. And your LSTM unit is 50, which is the representation of your A of t and C of t representation, which is equal to, the size is equal to 50 by 1. So the total number of model parameters for this architecture is 17,385. Let us try to run this architecture because it's a multi-class. It works like a multi-class, right? So which token out of the vocabulary, which token should get the highest probability for a particular given input sequence? That is what it is going to perform. So it is a categorical cross entropy. Here you can, as usual, you can try with a different optimizer here. So I'm using Adam here. So 500 epochs. Let me try and see the result, how it works. So gradually you can see the accuracy increases. But it gets saturated somewhere around 60, 65. It's not crossing 70. Even after 500 epochs, it is not crossing 70. Even you can try with the different optimizer also. You can try whatever the optimizer you change. Maximum it will not cross 70% because it's a vanilla model. Okay, it is. It's a very rote learning, right? Okay, for the previous word token is like this, the next token is like this. So there is no word order or there is no sequential context here. So maximum percentage it can learn. Even if you try to increase the LSTM neurons and word embedding representation, whatever you do, you cannot increase beyond 70%. So maximum is around 66 to 70. It's saturated. So how to validate the performance of the model? I have to present one input token, okay, because it's a one input, one output model, right? So my test input is, suppose the nice is the token. So whatever the data preparation you have done, should your production, let us assume this is my production data. Production data should go to the standard process. So tokenizer is an object already we have created. In a production environment, only there is no fit business in the production, only tokenizer.text to sequence. Only this will be done. So tokenizer.text to sequences, your production data is going here. It is being encoded. Once it is being encoded, it is being represented in the form of a numpy array, typecasted as a numpy array. Then you are asking the model.predict. Vocabulary got the highest probability, it is going to return. So you apply np.argmax for it, and that you represented as a y hat. So the y hat is a one hot encoded representation. It is going to return you the integer value. So I have to decode that index, right? That index corresponding to the corpus, what word it is associated with that. For that, you can ask the tokenizer to the word index dot items, because the tokenizer dot word index is going to return the corresponding word for that particular index. So it is going to return the index as well as the particular word. We are printing the corresponding word. If the index is matches with your y hat, we are printing that word. So randomly, I just you try to check with some random token for it. Nice. So what is which token should have the next highest probability for nice? It is given nice 2. When I give I need. Okay, one more time you run, any number of times you run it, gives I need. There is a chance that I can, okay, there are so many chances are there. But this model has trained for I need. But we have in the training records, we have so many combinations after I followed by. See, I would is there. Okay, I will is there. Okay, I need is there. So out of which, okay, this one-to-one mapping has trained in such a way that I need has got the highest probability. Suppose if I wanted to generate a sequence. For example, I given, it produced the need as the output. Now, once again, whatever the output produced by this LSTM model, once again, I wanted to feed this as an input. Say, for example, I wanted to feed this need as the input again. Okay, that means you can try to generate a sentence like this, isn't it? So again and again, you are calling the LSTM function, like model.predict, again and again, you are calling. So when I present I, model is producing I need, once again, I present the need as an input to the LSTM. Okay, when I present need as an input, it producing the output any. Suppose I represent that any as the input to the model. Let us see what it produces. I need any questions. Okay, likewise. So instead of manually I go and change every time. Okay, I'm going to do this process in an iterative manner. Okay, for that I just create one small user-defined function to do this process. Remember, your model is not producing the entire sequence. We are presenting the token again and again to the model just to comprehend what kind of sentence it creates. If I call the model again and again, whether it's creating a meaningful sentence or not. For that purpose, I'm just creating this interface. This is just an interface. You should understand that model itself not giving this the whole one sentence in one shot. So manually, whatever the value model predicts the output, whenever you see model.predict, you have predicted y hat value, and y hat value is converted again back to the output word. Okay, that output word is again presented mapped onto your input text again. Again, it is being presented in the form of input text again. So when the for loop is going again, it is going to pass your the input text, whatever the produced output word, like that is going again as an input text. According to the length of the sequence, whatever you specify, number of words, how many words you want to produce like this. According to the length, it is going to keep on in a loop. It is going to call this model.predict. It is going to be called in a loop till the length of the words you're going to generate. For that, the subroutine is going to work in that order. So we have started with the nice, right? The same nice. Now this time I'm calling this function generate sequence. We call the model, call the tokenizer, because we need a tokenizer to prepare the input to the model, right? So I need a tokenizer. So the starting token you are giving. So nice I give with the 10 words I'm asking to generate. 10 times you are feeding the value. Nice to you. I need any question. Sorry for the late. Look at this. It is not producing any meaningful sentence, isn't it? Because it's a very simple vanilla architecture. There is no word order. So whatever the sentences it produces also, there's not a meaningful sentence it produces. So we can understand it's a very preliminary model. There is no intelligence of the word order. So practically nobody is going to create such a vanilla model. One word input, one word output. Does not make any sense. Even for one word input, one word output, can I create a even feed forward model? We can very well build a feed forward model, isn't it? What I can do for a one word input, one word output, anyhow you have vectorized your input. The size of your input is a 10 by 1 vector. This 10 by 1 vector you map onto one dense layer with 50 neurons. Instead of LSTM unit, simply you can call the dense layer. And output layer based on your vocab size, based on vocabulary size. It is a feed forward model. No, still I can train this feed forward model. Still it is going to do a good job. Whatever the token you produce, it is going to see out of the vocabulary which token got the highest probability. It's going to return it. Even though I have used the LSTM model, but I have not leveraged the intelligence of the LSTM model. So we may not appreciate the intelligence of the LSTM model because you have not presented the input. It is not the mistake of your LSTM model. Here I cannot blame LSTM model because you have prepared the model like this, like a feed forward model only. We have not leveraged the sequences. Your input has to be presented in the sequence like xt plus 1. but you have only one word you have presented. So your result will be treated like any other feed-forward architecture. So there is no great intelligence of the word order. So in the second design, I wanted to create some word order. So that is my model 2 design. Okay. In model 2, I'm going to create a word order, something like this. So all possible combinations I'm going to create. So including 1-to-1 mapping. So nice to, okay, next record, training record will be like nice to, then nice to hear, nice to hear from. So every, because every sentences I'm going to give in a multiple way I'm presenting the record during the training process. So nice to hear from you. I'm going to train my model in the different variations I'm training. The first instance I'll present only one token. The next instance I'll be presenting the sequence of token like x of 1, x of 2. Next I'll be presenting like x of 1, x of 2, x of 3, the sequences. But make sure that LSTM will receive the fixed length. You have to specify what is the maximum length of your sentences, that you have to specify. So whenever you're creating the input representation with unequal length, I have to use this pad sequences. Pad with 0. So padding, using padding operation, I have to pad with the maximum. What is the maximum length of the sequence? The remaining I have to represent with 0 padding. That means your model will receive something like a 0 means the word is not yet started. Okay, it's a 0 input. So if everything input is 0, your memory unit is 0. So there is no memory for your 0 input. The next token also 0. So x is scaled by anything, it's going to be a 0. There is no memory for the 0. Okay, again it's a 0. Okay, here only the valid token is coming. This is where the valid token. Say for example, nice. Okay, for the nice. Okay, what is the next word? It has to be trained for this. Nice is the input. What is the output? Model will try to bring a relationship like this. The next time when you present nice to a word order, you present again here. The token is not yet started. Token is not yet started. That is how your model understand. Okay, the moment you presented this, it's a start treating this is the valid token. So this is x of 1. In fact, theoretically speaking, this is x of 1, x of 2, but literally inside, no major changes that happen because they are x scaled, everything scaled by 0. Effectively, you don't have anything happens. So effectively, the valid token starts from here, these two. So the next is 0, nice to here, like this, it will go inside. So all possible combinations we are presenting the input. Now, this kind of learning will be having more meaningful context. For that, you have to do the data preparation in that manner, isn't it? So for every sentence, I have to create these combinations. Okay, so based on the new line, okay, you can differentiate the sentence. In case if you are loading external file based on the full stop, you can segregate the sentences. It's not a big deal. Even if you want, you don't want to segregate the sentence by a traditional way with a split based on the full stop. Even you can make use of sentence tokenization using NLTK package also. So when you read a raw file based on the sentence tokenization, first you extract all the sentences. Then I can feed each sentences. Each sentences I can feed to create the combinations like this. So for line in data.split based on the new line, okay, tokenizer.text to sequences for the one sentence alone is being passed here. One sentence at a time. Okay, this is a one sentence based on the new line we split it. For the one sentence, the encoded value will be there. So we have seen for the one sentence, the encoded value is labeled like this: 29, 1, 29, 1, 30, 31, 2, I guess. Okay. So this is what a tokenizer will return. Here, the 0th index will carry the index representation followed by the what token it is. But here my this is enough to represent my word token. Actual word I'm not interested. So I put square bracket 0 to access only these information. So using this, you create the combinations. What are the combinations we create? 29 is the input and 1 is the output. Then 29, 1, and the output you wanted to create like 30. 29, 1, 30, and the output you wanted to create 31. Likewise, can you see it is creating the combinations like this. So for I in range, once again, 1 to length of the encoder. So here the length of the first sentence is the nice to hear from you, right? Before the new line. So before the new line, we have nice to hear from you. 1, 2, 3, 4, 5. Okay, 5 is the length of the first sentence. So here the length of encoder, the upper limit will be 5. Upper limit will be 5. So it will start with 1. So maximum I value will take 4. I value 1, 2, 3, 4 it will create. So encoded colon, okay, colon I plus 1. So for when I is 1, colon 2, that means 0th index and 1th indexes will be accessed first. Then when I is 2, 0, 1, 2 will be accessed. Then 0, 1, 2, 3 will be accessed. So finally, then 0, 1, 2, 3, 4 will be accessed. First you generate like this. Then we are going to pad with 0. And as usual, you can take the last entry will be taken as Y. And the remaining entries will be treated as X. First, I have to generate the sequences, whichever the way you are going to present your input sentences. Some sentences are a longer sentence, you can see, isn't it? See, these are some of the longer sentences. So for padding purpose, which is the longest sentence I'm going to feed to the model, that should be considered as the longest sentence. That many zeros should be prefixed to each input representation. So for padding, I have to import a library called pad sequence library, which comes from Keras utils package. See, padding of sequence is required here to ensure fixed length. So first I get my maximum length. So sequence in sequences, already we have collected all these sequences like a 2-dimensional list, isn't it? It is a 2-dimensional list, 2D list. So these sequences are already available. So I'm mapping for in sequences. Every time it is going to extract seq will extract this, next for loop will extract this, for loop will extract this. So I'm finding what is the length of it, and out of all the possible length, what is the maximum length to get the maximum. So maximum length, I think it looks like this. This is the maximum. Okay, I think this one is the maximum. So maximum length is 12. So then I call the library pad sequences. Each sequence you are passing. Okay, padding, pre-padding. All language models, we do pre-padding. Is there any situation we do a post-padding? Yes. We will be doing on another situations, we'll be doing a post-padding. Post-padding we'll be doing to the context of encoder-decoder architecture, particularly on the decoder side. In the decoder side, now it will be too early to comprehend this. The purpose of encoder-decoder is, in the place of encoder, what we use mostly, we use a typical language model. You know what is the meaning of a language model? This, whatever the designs we are using, it is a language model. The idea of the language model is to memorize the word order. Who's having the memory unit? A of t, and the C of t is having a memory unit, long term and short term memory. So based on the memory unit, it's predicting the next word. Whatever the sentences you pass, it is going to predict the next word. Okay. So mostly in your encoder-decoder architecture, in the previous session we have discussed what are all the application comes under encoder-decoder architecture. your one language to another language translation, or chatbot, or text summarization. So these kind of applications we use a encoder decoder architecture, even speech to text, text to speech. So in the encoder side, mostly we use, if for example, if you are doing this encoder decoder architecture for the text based application, in encoder model, we'll be using the same language model. So naturally your pre-padding we do. But on the decoder side, the role of the decoder is your decoder should start generating the output from the beginning onwards. Okay, but you can encoder but can wait for the valid token. If you say 0, it's an invalid token. 0, it's an invalid token. 0, and here onwards you are presenting a valid token. Start memorizing. Okay, start memorizing the sequence. Valid token, valid token. So you pre-padded with 0, and you start feeding a valid token like this. Your encoder will start memorizing the moment you start presenting the valid token. On the decoder side, what you are passing the information to the decoder, I'll be passing C of t and A of t memory unit to this decoder. Anyhow, we will be discussing in detail about this encoder decoder application to a particular application context. We'll see. Just quickly, I'm just giving you the idea of the role of post padding. What is the logical sense for the post padding? What context post padding will come? When you prepare the sentences for the decoded sentence, okay, for the given input sentences, this is the, say for example, if it is a language translation, assume for the given how are you, okay, the corresponding some other German translation or French translation, your translation should start immediately. Your decoder should not give 0, 0, 0 from here onwards this translation. This kind of design, it's not a proper design. At the decoder side, immediately start giving the translation. Translation started, then finally you pad with 0, which indicates that, okay, this is the end of the sentence, followed by 0 padding. So when you prepare your training record, when you prepare the training record, the encoder side and the decoder training record, not all the input output length will be the equal. Say for example, my English sentence is this. My maximum size of the English sentence is, say for example, this is the maximum length. This is how you prefix with zeros. But on the other side, decoder side, your corresponding translation for this T3 English token, maybe only 2 tokens will be there in a foreign language. Okay. 2 tokens. Sometimes according to the lexicographic, say for example, when comparing to English and French vocabulary is nearly 3 to 4 times the English vocabulary. More or less, if you look at the French grammar, the French language is very close resemblance with Hindi. Because in Hindi terms, we have, even for the non-living things, we have gender associated with the non-living things. There are certain things you end with E, okay, E symbol, and according whether it's a masculine or you're representing the feminine. Similarly, the French token also will be like gender wise, even for the non-living things also, it has some gender associated. So the vocabulary, but for the English, it is common. Okay, whether, so for every object, even for a non-living things, we call it as a it, that's all. It is, we refer it for the non-living. But for the French token, like a Hindi language, has a gender representation. So if you look at the vocabulary for the French is nearly, when compared to the English, the vocabulary is nearly 3 to 4 times. For even for a shorter English sentence, the corresponding French translations may take some 5 or 6 tokens. So that is an example we'll be seeing for the next case study, encoder decoder model. So in that case, your decoder side should start doing the translation from the first token onwards. Your translation should start. So during the training process, okay, the corresponding translation, okay, this is the corresponding translation in the output side. Say, let us, this is my Y1, Y2, Y3, Y4, the corresponding translation, and that's all. So afterwards, so this is the my end of sentence. After end of sentences, afterwards you can do the post padding with zeros. because output side also the longest sentence, whichever is the longest sentences, based on that you post padding 0. What is the logical reason for the post padding 0 here? Because at the decoder side, you have to start generating the sentences. But at the encoder side, your encoder can wait for the valid token. Whatever the valid token, it's still see invalid, 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 invalid. You start presenting the valid token. So your memory starts from here actually. But on the decoder side, immediately my translation should start immediately. In the translation side, 000 looks meaningless. So you do the translation till the end of sequence, you do the translation. So in a production environment, you will be presenting your input sentence with a fixed length. Okay. Say for example, how are you? You specify how are you. According to your training size, it will automatically do the pre-padding according to what is the maximum length of your training record. It will do the pre-padding, and it will be presented to the model. So your encoder decoder model will start doing the corresponding translation immediately from the first token onwards. Your translation starts, and finally it is going to give the last token at the end of sentence. So it is indicating that I have completed the translation. In a production environment, it won't give 000. Okay, only during the training side, because to maintain all the output sequences to be the fixed length, like how we present the input sequences to fixed length. In the encoder decoder architecture, output sequences also we have to maintain, because it's a many to many, isn't it? Many to many mapping. So for the many to many, my output length also I should maintain as an equal length. So in order to maintain equal length, I will be doing the post padding for the decoder side. So your language model is considered as a is an encoder alone architecture. You can treat it like an encoder alone architecture, encoder only architecture, encoder decoder. What we are using, this encoder only architecture, we are using this encoder only architecture for the language model, word order. If this is the sequence of numbers or sequence of words, okay, you are using the language order to predict. This model will learn to understand the sequence of this order. And a standalone decoder model, if you build any, see at the end of the day, your encoder is again LSTM, and the decoder also is an LSTM. It depends upon how do you present your input and output. It's going to act like that. Okay. If I use a standalone decoder, it is going to behave something like a trigger token. You start a trigger token, and this guy is going to generate a sequence of output. That means if I use a standalone encoder only architecture, it will consider as many to one, isn't it? Many means it is trying to understand the word order, and it's trying to predict the output. That is how it is being trained. And your decoder and only architecture is trained in such a way that once it got a trigger token, it is going to generate the sequences. This decoder only architecture is considered as one to many. If you construct encoder and decoder architecture, that is called as many to many. Okay. So what we are doing is, whatever the application we are seeing is, you can comprehend as a standalone encoder type of architecture. Standalone encoder type of architecture. Even I can extend the same idea to the numerical data forecasting, right? Your numerical data forecasting also many a sequence of numbers. For the sequence of number, what is the forecasted value? You can create this. So based on the forecasted value, again and again you feed to the model, you can generate the sequence of the forecast. That's not a big deal. That is the user interface that you can create. Okay. But primarily how you design your model is based on many to one. But in what way you can use it in a production environment, whatever the value it produces as output, the same value again you feed to the model to generate the continuous value for your forecasting that you can generate. Now let us see what this pad sequence is doing here. So this pad sequences, the individual sequences I pass with the maximum length, and you specify pre-padding. Okay, as soon as you run this, you can see all the sequences, how it is being padded. See, the first one is 29.1, right? 29.1. 6, all are pre-padded with zeros. So all zeros Okay, 29.1. Next is all zeros, 29.130. If you want to look at a specific 13, 32.8. 13, 32.8 is one of the record. Okay. Okay, let us verify this. I think ninth sequence. Look at this. For this guy, only 5 zeros are padded, pre-padded zeros. So once we have done the padding, okay, zero padding is done. What is the next step? Leaving the last one, the remaining, all the remaining should be go as the input, right? X of 1, X of 2, X of 3, X of 4, X of 5, X of 6, X of 7, X of 8, X of 9, X of 10, X of 11 here. According to the maximum length, whatever the maximum length, it will go to that. So only the last entry should be go to the output as my target. So -1, I'm accessing -1. The remaining except -1 colon comma. Okay, upper limit -1 means this is not inclusive. It is going to access till 34th index for this exam. Similarly, for each and every sequences, it is going to extract X and Y. As usual, your Y should go to 1-hot encoding representation. So your data preparation part is done according to second type of model. Okay, so many to one design. So the rest other architecture remains same. Okay, you look at your core architecture. I have not done any changes. What is the only difference? Your previous architecture, the input length we have given 1. Okay, but here we are giving the input length, maximum length -1, because the maximum length is including the output also. So I have to subtract 1. So maximum length -1. So in fact, what is the maximum length of our input sequence? 11 tokens. Only this is the difference. But rest other things, I'm using the same architecture, LSTM with 50 neurons, softmax, same Adam, 500 epochs. Okay, let us try this. This time we have more meaningful representation. You can see our accuracy tends to increase beyond. Earlier architecture got stuck somewhere saturated around 66%, isn't it? Now can you see the accuracy goes up to 94% with 500 epochs.
Sir, one question.
Yeah.
Will the model work if I don't do embeddings and pass the tokens as it is? Like, will the model work, the LSTM model, if I don't do embedding and pass the tokens as it is, like 29,1, 31, 30? So will it be able to predict without the embedding structure presented?
What is the even the bad representation? What is a bad or poor representation of a token? Even I don't use the word, is a very poor representation. What is the poorest representation of a token? Suppose you have a vocabulary of 50 words. Okay, 50 words. When you are trying to say that, okay, the 50 words, say one of the word is a nice, can I represent with 7, you're asking, isn't it?
Yes.
This is something like a nominal encoding, isn't it?
Correct.
Number has no meaning, isn't it? You have some meaningful representation. That is the reason I go for the 1-hot representation. Out of the 50 location, okay, you are saying that the nice, the position of nice is this. The position of hello is this. So that is the average representation. But the best representation is whatever the feature has a dense meaning. Okay, some meaning, no meaning. I'm traveling from the no meaning representation to some meaning representation to the dense meaning representation.
Okay.
Just like your basic your tabular data set, how do you represent a category?
Hmm.
Suppose I have a category of a vegetarian, non-vegetarian, vegan, and so 3 categories are there. When I say 1012, how model will treat this input? Model will treat the number 2. Okay, number 2 does not carry any weightage. For example, 2 is being represented for the vegan. Just because vegan is given higher weightage, your model number, actually this 2 does not carry any meaning at all actually. So what we do pd.getDummies. After creating a getDummy, say for example veg and non-veg, whenever you have a veg representation, present of veg, absent of non-veg, okay, and absent of veg, present of non-veg, neither veg nor non-veg, this is the representation for the vegan. So model understands this representation as neither this category nor this category. So it has a meaningful representation. Number 2 does not carry any information. This is a nominal representation. Nominal representation does not, number has no meaning. So this is a one-hot representation. Same manner, when you specify your token with a number 7, it's treated as a nominal value. This number has no meaning at all. Hope you got it.
Yeah.
This time I wanted to evaluate the model with the seed token, nice. But the second model, you can present more than one token, isn't it? You can present more than one token. Nice to hear. How many times you wanted to represent the data? So when I wanted to use it for only one time. So nice to hear from. So the next token it predicts. So when you write an email, when you try to start replying, how do you write? Nice to hear. Once you wrote nice to hear, try to autocomplete like this. So next to 2 words, if you want to generate. So nice to hear. Okay, the next 2 tokens, next 2 times you're calling the function recursively and calling the function again. So this time, number 2, it indicates what? Actually, literally, I am feeding. Okay, whatever the value is being predicted by the model, I'm feeding that as a 4th token. For the second time, I'm calling the same function. Second time, we are calling the same function. This time, we are actually calling the function nice to hear from. That is equivalent to you are calling the function for one time. So when I feed this nice to hear from, it is generating. Okay, so you should understand how to operate this. Okay, the second, whatever the value you are giving here is how many times you are calling the function. Whatever the value it produces. Suppose initially I start with a nice one token input. Okay, one time I'm calling the function with one single token. It produces nice two. Let me start something with I. I will. Okay, I will. Whereas your previous model, when I start with I will, when I call this for multiple times. Okay, let us see what kind of sentences it produces. Okay, we have presented nice for 10 times. Nice to you, I need any questions. So meaningful sentence. Okay, let me just quickly generate the sequences starting with I, capital I. maybe I just feed this I 5 times. What is the next? When I do it for one time, what is the next token generate? I shall. Okay. That means when I give 2 means what is the meaning is shall is given as the input again to the model because it's a 1 token input, 1 token output. So the meaning of you pass 2 means you are passing the shall when I pass what is the output. It is equivalent to running this guy, the same thing. Like you pass shall as the input and you're asking the model to give me the output. You should know how to operate this function. Okay. So when I pass shall, it is giving me the output reach. Okay. Likewise, if I give a seed token as I'm asking the model to generate 8 times I present this. I shall reach out to you, kindly call me. Okay, not bad. Okay, somehow meaningful. Some other part of the sentence that try here. Okay, it I'll try with it. We okay. These two key tokens, seed token, let me try it and we. Okay, few tokens it gives a meaningful sentence it create, but few seed token it is not creating a meaningful sentence. Let us see the second model. If I give a seed token nice, what kind of sentence it create? Nice to you, kindly call me. It was pleasure. So the second so every time the sequence generations, this portions it's different, right? You have to update that portions. Otherwise, you're going to take the previous representation. So every time you have to modify the sequence representations. Modify this and build the model. Since actually yeah, otherwise better you can name the previous model as model 1 and this model is model 2 or generate sequence 1 and generate sequence 2. No need to run every time. Nice. Likewise, you can validate with the different seed tokens and see how well your model recognizes. See here, I am giving only the same training record. So it looks like your model is doing even a good job, even with one token input, one token output. But for some other sentences but make sure that all the language model will try to accommodate all standard tokens. Here we were using the unique number of token is around 84, right? But your large language model will be using billions of words. So almost all possible words available in the dictionary. Okay, any word is not part of this. If you try to give here, we have the token please is available. Please feel free to reach out to me anytime. Okay, this gives more meaningful. Suppose okay, it can predict anything after the. See, to connect with you evening with training. And so there is no token in my corpus like girl. Okay, let us see what kind of sentence generate. Girl to connect with you, you to you. Because the model has not trained all possible type of sentences in the corpus. Very few sentences only I have randomly picked from my email conversations. So for a production level language models, which uses the billions of sentences, it has been trained, and the vocabulary sizes will be in the form of 5 billion words. Even the GPT-3 model, which is the chat GPT is using in the backbone, uses more than 5 billion words. It's being trained on those. So all the words in the vocabulary, the standard vocabulary, it will train it, and most probable, what should be the most probable, the next word has to be predicted. Your model will try to give it. The drawback of what is the advantage of training the model with many sequences with one word, okay, x of 1 model, and you produce one token. And another case, you x of 1, x of 2, x of tx you present to the model, and you're generating the output. The benefit here is this model. Okay, this model will always work with, even though you call this for 5 times or 8 times and all. This is just you're calling the model multiple times. There is no, this 8 or this 10 is not the, here there's no intelligence. Okay, here there is no intelligence. Just you are calling the model multiple times. But every time you call the model try to produce the output based on the one single token. Okay, does not carry the information about the past. Whereas when you train the model with the sequence of words, okay, whatever the probability, the next token, when you present some sentence like you are giving some context. Okay, if you try to give the a context like this, the girl walking, now it is going to give a meaningful output for this. So what is the probability of the output y cap of t given the girl walking? So your past memory plays a role here, because when you give a sequence of sentences. But here there is no scope of a past memory. It's a very crude learning, one-to-one mapping, just like your feed-forward model. So when you in real-world situations, we don't give a single token here. Of course, you'll try to give some context. Based on the context, you try to do the autocomplete for it. So presenting this number doesn't, you are presenting the same, whatever the output is being produced, you are adding, that is the additional context. Okay. For example, the girl walking. Okay, the girl walking in, or the girl is walking near a seashore, or the girl walking near a seashore, or the girl walking in a seashore. Likewise, when you try to give a context, it is going to produce the what is the next probable word. So here we just to generate the sequence, here I'm passing the number. Meaning is whatever the word it produced or predicted by the model, that word also will be appended here as part of the length of the sentence because the predicted word. The girl walking near, you have given this as the input sequence. The girl walking near a seashore. It try to give this output. So you can again feed this as a part of the input, and you can ask what should be the next probable word like that. So the model is highly dependent on the kind of tokens what you have been trained, the combination of the tokens. Any token which is not part of your training record model, you cannot expect the model to do the magic for you. After all, any deep learning model will try to behave based on the kind of training records how you have presented. So since there is no token, you have, even though it is a sequence of word order you have given, okay, your model could not comprehend, okay, anything out of this. Say for example, I have given the girl, because the second model can understand the sequence. The girl to connect. So you can see based on the training corpus only, it is trying to auto-complete it. So it cannot generalize this, right? Imagine if you have a large volume of a data set and it is generalized it, and try to give more meaningful sentences for this. Finally, one more variations I have given here, fixed length. Instead of variable length, okay, this is another design, fixed length. So again, I would personally consider the second model is better than the first and third designs. Okay, just to give a 3 variations to analyze the performance. The second variation, all the input I have prepared like a 2 token input, 1 token output. Just 2 token input, 1 token output. So second model, you can give the input more than 2 token. I would like to give this for 2 times because the longest sentence itself 12 only. So here I give this, I would like to. But the first model can accept only 1 token as the input. But on the other hand, the third model can accept only 2 token input. But this model can accept the input even up to the maximum length of 12 token input. So your LSTM will have the memory of what is the context you are talking about. So this is the third design with the 2 token input, the same procedure. Here again, the maximum length is of the sequence is 3, but including the y it is 3. So I should subtract 1 out of it. Maximum length minus 1. So the third model is going to receive the input length to the size 2. So again, this model also is going to give a meaningful sentences to anything part of the training record. It gives a meaningful results. You can see the accuracy score is crossing 95% for this, and gives. Earlier, I trained with one of the popular nursery rhyme. Mary had a little lamb. This rhyme was very popular. So earlier, I tried with some of the popular sentences. When I give a C token as the lamb, okay, in the rhymes, one of the sentence in the rhymes, you can see these sentences as well. The Mary had a little lamb rhymes. Fleece was, as I give as a C token, it was giving as a fleece was white as snow and every. This is as a part of the poem. The lamb was sure to go. It followed her to school one day. Okay. So earlier I trained the model with the Mary had a little lamb poem. The complete poem I trained it. some part of the poem and give us a seed token. I wanted to see how it generates the poem, how closely it generates the sentences of the poem. I just verified it. But anyhow, here we are training to some email conversation. Any example you can try, and you can see some interesting results. To what context you wanted to train a language model, you can try to see the performance of these three architectures. See, the third design, whenever I given I would as the seed token, I operate this for 9 times. I presented this. So first model, I would like to discuss possible training sessions with your organization. So personally, we can rate model 1, model 2, model 3. Mostly in the language model, okay, the judgment is based on very qualitative. Okay, tomorrow I'll talk about a metric called BLUU, blue score. So what is the expected target and what is the your model has produced it? So it is like a unigram matching, how many bigrams matching, how many trigrams matching. Based on that, we have a metric called bilingual evaluation unit metric. We have called it the blue score, BLUU score. But most of the occasions it is done very qualitatively, subjectively. Apart from subjective, and this blue score also is being used for the validation method. So in this design, M1, M2, M3, definitely first model design is a very poor design. Third also, I'm not suggesting as a good design. So model 2 is a good design. In model 2 also, yeah, sorry. Yeah, I was thinking to do some modifications. Model 2, yeah, model 2, whatever the design we have done, it's reasonably doing a good job. So out of the 3 architecture, I would recommend to go with the second architecture. So second architecture is a very good design. Even you can the length of the sentences, even you can increase it even more than 12 tokens. Longest sentence also you can view, and you can see how your model performs. Can you tell me this language model? Language model comes under which what kind of design is this? Already I told you this language model can be interpreted as encoder only architecture. It behaves like an encoder only architecture. So what is the nature of the encoder only architecture? Encoder try to understand the language order and try to memorize the language order in the form of memory units. But in the language model, we are not using explicitly, I'm accessing cell state as well as the hidden state HT or even book notation AT. We were not accessing these, isn't it? But in the encoder decoder design, we have to access this. We have to access this. Why I need to access this? Because these two guys should go as part of the input to the decoder model. This is going to act as a trigger. Okay, because your LSTM model also consider as a standalone language model. But what is the major difference? This decoder side, you have given some English sentences. Your model has learned and memorized this the sequence of the English sentences. Okay, for these English sentences, you have trained another LSTM architecture to generate a French translation or a German translation or any other foreign language translation. But for this guy, whatever the English translation memory, your short-term memory and long-term memory, that will be fed as part of the initial state, isn't it? So usually this model, when it starts with, there is no initial state. Start with all zero. Long-term memory and short-term memory all are zero. But for the decoder side LSTM, my initial state will come as a whatever these A and A of t and C of t from the encoder output will be given as part of my initial state along with my trigger token. So your trigger token will be like a start of sentence, SOS. So this model will start generating the translation for this, or even a chatbot also. You think about a chatbot application. Okay, what are the courses your organization is offering? As a chatbot, this is going to give me the answer for it because already been trained for some standard set of sentences. So for this sequence of English sentences, your decoder will start generating the output sequences. So this is going to be as a memory unit. Along with that, your trigger token, start of sentence. Your decoder will start giving the answer for it. So this is the right hand side portion is called as a one-to-many design. Okay, this left hand side portion is called as many-to-one design. Combination of both is many-to-many design. Many-to-many design. So your input sequence also, it's you have an English sentence or your question to the chatbot. Your output also going to generate the sequence of sentences. You can also ask this, sir. Here also you are passing many token as the input and output also many token output. Don't consider literally. See, here I'm calling this at one point of time. My LSTM unit is generating one token at a time. Please understand. At one point of time, our LSTM unit is predicting one token, one future token at a time. Since I'm calling this function recursively for 9 times, you are feeling like it's generating the sentence like this. But internally, the architecture generates one token at a time. But the loss function is calculated based on y of 1, y of 2, y of 3. The total loss is based on the individual losses. But as a practical use, when you consider your LSTM model is predicting one token at a time. Can you able to comprehend this? Don't think this application also superficially it looks like this also many input I'm giving, output also giving many output, but literally it is generating one output for this. How to really you can verify this? I have to pass just one to this. The third model I didn't try. Okay, the recent model I have trained here is this. Okay, I would like to, when I feed this as the input, I would like to, my model predicts one token at a time. So it is a many-to-one category. So it works like a encoder only architecture. So when I put 2 means how this model is working, the meaning of 2 is what we have done in the subroutine, whatever the value predicted by the model, which is the token predicted by the model discussed, right? This CUSS. I am appending that as part of the input now. I would like to discuss. Now, if I'm operating the LSTM model for one time, now I would like to discuss will go as an input. What is the output produced by the model possible? So every time I no need to go and modify this manually. Instead of that, I just say that 2 times. Okay, I just feed this is the input. I would like to. So it is generating. It looks like generating multiple tokens for it, but it is. I'm operating it for 2 times. So I would like to discuss the next time when I operate. I would like to discuss is the input. What is possible with output? Can you able to relate this many-to-one? So I would like to quickly show one more example for the numerical. For the numerical data is very straightforward. In fact, your data preparation is not that cumbersome as like what we have done for the text data set. One exercise I have done for a numerical forecasting problem. Generally, a numerical forecasting problem, if you came across your traditional machine learning, you are familiar with AR model, autoregressive model, moving average model, ARIMA model, SARIMA model. All these models are linear models. Please understand, they are linear models. That means, suppose your time series data set having some kind of a trend. Say, for example, there is a rising trend. Suppose I'm working with the sales data or airline passengers. For the last 10 years, airline passenger data, if I see, okay, 2010 till 2023, the pattern will look like this. This is increasing trend. So year by year, the number of airline passengers proportionally increases. This is a rising trend. And some weather data and all, it shows some seasonality, isn't it? Indian weather during April, May, March, it increases to the peak. Okay. And beyond August, September, it's coming down. And again, next year, April, May month, it goes to a peak and come down. So what we call this is seasonality. Seasonality in a time series data. If a trend or seasonality in the data, your linear model cannot handle this. So why it got the name autoregressive integrated moving average? Internally, actually, what they do, they apply a transformations. What kind of transformations? Very simple transformation. Just you take a first difference or second difference they take. First difference is nothing but x of n plus 1 minus x of n. Second difference is x of n plus 1 plus x of n minus 1 minus 2 times of x of n. Because literally your time series data set is considered like this. Okay, this is x of n plus 1, x of n plus 2, and so on. They try to apply the difference equation. Whenever you take a difference, actually it will try to detrend and deseasonalize your data. Once your data is detrend and deseasonalized, they try to build a forecasting model to the transformed series, not on the original series. Okay, the standard model where they'll apply the forecasting model to the transformed series. Because your linear model can handle only a time series without having any trend and season. So these transformation will try to detrend and seasonalize. So for the transformed series, it try to predict the next value. So once again, it do the reverse transformation. What is the opposite to differentiation? Integration. That is why it got the name integrated moving average. The meaning is internally this function will differentiate the data, and then it will build a forecasting model, and then whatever the value is being forecasted, it will do the reverse transformation, give the value in the real units. So that is why it got the name integrated. So the term moving average is meant for, they apply some first order or second order filtering to smooth out some noise component in the data set. Mostly first order moving average, second order moving, something like your CNN layer. In CNN layer, we are operating a filter, right? Mostly in CNN layer, we interpret as a edge reduction value, turning points. But particularly in moving average, they try to operate in the first order means 1/3 of box filter they'll apply. So every 3 samples, they try to average the 3 samples so that a short variation in the waveforms and all, make it as a smooth variation. Suppose the variation is like this, they make it as a smooth variation like this. But original pattern it will preserve. See, for example, this is the original pattern going up and going down like this. But your original data having a slight fluctuations like this, a slight fluctuation. When we apply moving average, what happens after applying the moving average? It will be like more smoother, like going up, coming down, again moving up like this. So that is the role of moving average. And autoregressive, it's something like your model is behave like a linear model. Okay, your y cap t plus 1 as a function of, okay, your past, how many lakhs you choose. Suppose if I take the past 3-day temperature, so y as a function of y, right? Here your same temperature is acting as your dependent variable and independent variable. Unlike your tabular data set, okay, you have x and y. So y as a function of x. So y cap as a beta naught plus beta 1 x1, beta 2 x2, and so on in a regular regressive. But this is an autoregressive model. That is why it got the name AR. So I can say that, so y of t minus 2 beta 1 time of plus y of t minus 1 times of beta 2 plus beta 3 y of t. So past 3 lakhs I have taken. along with the intercept beta naught. This is how your auto-regressive model works. It's a classical model. But here I can directly replace this classical model with the LSTM architecture, just like your many to one representation. One of the crucial thing in this design is, if you look at in terms of code, it's very simple, just 3 lines. One of the success of this many to one forecasting model using LSTM model is, you should have a strong foundation of understanding the time series data, your domain knowledge. What is the domain knowledge I was talking about? What is the trend, the seasonality? Okay, how do you smooth the noise in the time series? And also, if you have a specific domain knowledge, that also say for example, here we are applying on to the stock market trading. That domain knowledge also plays a very crucial role in choosing the lags. In our previous exercise, we were taking what is the maximum length of the English sentences we should consider, isn't it? Similarly, for this application, how many days of lags if I consider, so that I can predict the next day stock value in more meaningful manner. Even if you don't have a domain knowledge, we have a methodology like autocorrelation plot and stuff like that there. But in spite of this autocorrelation plot and all, your domain knowledge also plays a crucial role. Generally, what we do, whether it's a temperature or a rainfall data, simply you see the autocorrelation plot. When you look at the autocorrelation plot, the logic is very simple. Like a lag 1, lag 2, lag 3, it will try to shift your data set and try to perform correlation score. Okay, why it got the autocorrelation? Because I have only one column. Say it's the temperature. So temperature time shifted 1. That means what? Today's temperature. Say this is today's temperature is. It's a time shifted 1. Yesterday's temperature correlated. And this is yesterday and day before yesterday. So one column, another column is the time shifted 1. These 2 columns correlation is done. Say for example, your correlation score says 0.4. And maybe at 7th lag, maybe you got the highest correlation is around 0.65. So from your time series dataset, you can understand your time series dataset having a very good correlation with which lag. So that will vary from one domain to another domain, isn't it? Even a particular stock value of a particular stock value follows a particular pattern. Some other stock value follows another pattern. Your gold price follows a different pattern. So if there is a person who's literally day in and day out, literally they are in that field for many years, they can able to figure out some characteristic of that the value in what fashion it varies. So some of the agents in the stock market trading and all, they can clearly tell that the stock value for every 15 days it will experience a rise and fall and so on, isn't it? So and again, the gold, if you are a gold trader, many jewelry shops and all, they purchase the gold, they have some kind of a predictions. Okay, during this month they will purchase the gold because the prices go down and they make profits. So if you have a domain knowledge, you can choose the number of lags. But however, this data set I have done an autocorrelation plot. Yeah, partial autocorrelation plot is different from autocorrelation plot. Partial autocorrelation plot will try to suppress other autocorrelation effect whenever it's trying to concentrate on one particular lag, try to highlight on one particular lag, which is the dominating lag. So that is, if you wanted to see all the lags, if you want to see the score at all possible lags, ACF is recommended than this. So it is going to highlight on which is the best possible lag, PACF, but ACF is preferred to see all possible lags. So even if you don't have a domain knowledge, use the autocorrelation plot and choose the number of lag. But for this Google stock price, I have taken 60 days lags. How I chose, I don't have any domain knowledge on this trading and all, but I have taken autocorrelation plot for this, and I have chose a 60 lag as the best lag for this. Even you can try with a different length of the sequence for this. 1 month also you can try, or even 10 days also you can try. So which lag gives the best score, you can go with that. But remember, whenever I treat this as a numerical problem, remember your LSTM model works as a regressor. Your loss function should be different because it's predicting the value, numerical value it predicts. Whereas earlier in the word, it is actually predicting the probability of the particular word, the vocabulary. So we use categorical cross entropy, but here it is a mean square error is a loss function. If you want, you can download this file. This is one of the interesting time series. I have tried both linear model as well as a non-linear model, which is LSTM model. That is why I have taken this example to demonstrate a numerical problem. So one exercise we appreciated for the text data many to one. Okay, this also comes under many to one. Many to one, because based on the 60 lakhs, we are going to predict the next day value. So if you load the data, okay, there's so many columns are there, but here I'm going to consider the open price of stock value each and every day, open price. Any variable you can forecast, but I have considered open value here. So I have scaled the data, my input sequence time series data set. I have scaled it here. I have done min-max scaler. Again, the scaling choices, any kind of standard scaler also you can do. So this is the place I prepare the input output sequence. As I told you, right? For problem to problem, how do you prepare your input and output? That portion alone vary. But your core architecture, if you look at the core architecture, just the 3 lines of code. Just the 3 lines of code. So here I'm going to prepare my record like every 60 samples. I'm going to keep it as X, and the 61st sample should be Y. Okay, now I look at the first value of the I index is 60. So 60 minus 60, actually 0 colon. I'm going to start with 0 colon. Okay, till 60. That means 0th index, 0, 1, 2, it goes up to 59. It is going to consider, it's going to append in X. What is going to append in the Y? Corresponding target for this 60th index, isn't it? So from the same training set, scaled version of the training set, it is accessing 60th index. Directly I'm passing here I 60, 0. So the 60th location value I'm accessing. So this is your X, and the corresponding Y is the 60th index. So now I increment to 61. Next, your I X value is going to start from 1, it goes up to, because here it is upper index is 61, so it will go up to 60, and Y value is the 61th index. Likewise, your entire time series is going to create, how many such sequences it is creating? 1198 sequences. Look at the length of each sequence is 60. And remember, already we have processed one time series data set. Hope you remember brain signal, isn't it? But our CNN layer, one-dimensional CNN layer, we have passed CONV 1D, convolution 1D. There also we used the time series data set. But remember, whenever we feed the time series data set to the model, your TensorFlow, you have to represent this as a single channel or multi-channel, like for the images. So you have to reshape it, and you have to tell that it's a single channel. So let me create the input output sequences. After creating the input output sequences, we are preparing the data like this. What's the meaning? Every input 60. What is the length of each input? 60, but it's a single channel. So you're modeling, you start with the sequential. There is no embedding layer because the numerical data. Straight away you go and define your LSTM with 100 neurons. Look at my input shape is nstrain.shape square bracket 1. Okay, this is square bracket 0. Anyhow, number of records is not mandatory, but you have to pass these two ways. I have to pass this. So what is the 60 is the how many lags, the actual length of your each sequence. And the last entry is telling that how many channels, a single channel. If you want to, you can introduce a dropout to bring some kind of a regularization. And look at the way I have designed the output layer, just only one unit because it's going to act as a regressor. Look at the last function I'm using is a mean square error. When I train and validate this data set for the validation data set, a separate file is given for the validation data. Actually, the training data has the data till 2016. Okay, you can see the training record starts with January 2012 and goes up to 2016. 12, 13, 14, 15, 16. Okay, 5-year data I'm using as a training. And 17th year, I'm going to use it for the validation. So that is being kept as a separate folder. Stock price test. So 2017 record, I'm going to use it for validation. So your validation data set also you have to prepare. So totally I have only 20 records are there. The validation records, 20 records. 2017, 20 records are there. But remember, say for example, this is the validation record. 1, 2, 3, the value goes like this. Okay, this is the actual. Now I'm going to use the LSTM model to predict this guy. Okay, to predict this guy, I need what was the recent 60 lags I want, right? Naturally, I should fetch this guy from my training sample source. My input should come from there. Because the validation data starts, say, for example, it's starting from the 2017 record, I should take the last December and November record of 2016 will come as my input. Because 2 months, what is my past value? So that value I should access from my DAT train. Okay, DAT train, I should concatenate that 60 records. So after concatenation, this 60 records and this 20 records put together, it become 80 records. So for these 80 records, I have to create the sequences. How I can create a sequence? The 60 record is going to be act as my X test. What is my Y test for this? This is the known value. And my model is going to give the Y cap. So what is this Y cap and what is the known Y value? I can compare this, isn't it? Similarly, the next sequence is how I'll access. Next 60 records, you'll have to do a time shift of it. Okay, this 59 and this first record already is known to you, right? Next, this 60 will be acting as my input. That is my 60. And for that, what is the next value? What is the actual Y value and what your model predicts? You can compare these two things. Similarly, you can, how many such sequences I have created? Like 20 such sequences because you have 20 values in the validation folder. So 20 samples are there. So you can create such 20 steps you can create for your validation data. And if you ask the LSTM model for model.predict for this validation, whatever the sequences in the validation data, it gives the, for the 20 records, it gives the prediction score like this. I plot with the actual and the forecasted value. The blue one is the forecasted and the red one is the actual. Of course, some deviations are there, but you don't believe in the same time series data set. When I tried linear model, ARMA, ARIMA, all possible models I have tried. And the score the mean square error score for this. So the stock price was predicted with the average difference of more than $50 in the linear model. 45 to $50, $45 to $50 with the average difference, because RMSE score reflects the average difference, right? And what average difference you're modeling. But with the non-linear model, LSTM model could able to predict this with a difference of $15, with the average difference of $15. And more than that, the blue one is the forecasted value. More or less, it follows the actual pattern of your time series. That is very important. The good thing is, even though it's maintaining a good average, at the same time, look at this, it's maintaining the pattern between this first to 5, 6 values. It is a rising trend. Your blue one follows a rising trend. Okay, next another 10 samples, there is a constant, there is no fluctuation. So it's maintaining the constant. Again, the last few values, again, there is a rising trend. In fact, it does not exactly follows the red one is the original, but your LSTM model can almost precisely, closely very follow this with the average difference of $15, and more or less it follows the trend. Actually, your linear model, I just draw the linear model, how it will give you the graph look like. Suppose if the red is the actual, okay, red is the original, your linear model would predict like this. It does not follow any trend. It's a linear fashion. It predicted. Look at this. It is not following the trend of the data set. And overall average it maintains with the original series is around the $45. Whereas our LSTM model forecasted with average difference of $15. Same idea, many to one idea, you can extend for a numerical data forecasting also. What is the only change I have done? You have to change your cost function as a mean square error. But otherwise, same architecture and also your data preparation part. So according to your time series data set, how you should know how you have to prepare the sequence of the data. So here, which one is very crucial? How many lags you have to take it? That will based on autocorrelation plot or with the help of a domain knowledge. You can even ask the client also to have a domain knowledge. Interact with the client and choose an appropriate lags, and you can build a model. Even I tried with the different lags like 1 month lag and all, 30, 40 and all, I tried it. But I got the best score with 60 lags, I got the best. You can also try with some different lags, even more than 60 lags also you can try. But what is the best score I have got for how many lakhs I have got? I have reported.